A common question among incoming engineering students is how much math is there in engineering? And this is a two-part question. How much math is there in the engineering curriculum in college, and how much math is there in the real world when you start working? Well, during college, there's a lot. Most engineers will have to take calculus 1, 2, and 3, as well as linear algebra and differential equations at the minimum, then apply many of those concepts in your classes to engineering problems. But in terms of how much math you use after college, it depends. And I want to explain these differences, but focus on the after college part. I went into detail about the curriculum in another video linked below, but now I want to compare it to what you do at a job. Now for those who are impatient, let me just summarize this whole video right now. Based on experience asking around and doing a lot of research online, it seems like most engineers almost never use calculus after college. If so, it's rare. They use computer software to do the real advanced math. Almost all engineers do use math, but it's normally either algebra or linear algebra, trigonometry, or statistics throughout their career. Also, many engineers say that a mathematical foundation on the more advanced math is important because you do apply those concepts even if you don't do the rigorous math itself. And something I saw a few times that I do agree with is that you need to have a mathematical understanding so you can verify that the software is giving a correct result. This doesn't mean you have to prove everything is right, but you should be able to provide some verification. Now there are millions of engineers out there, all with their unique job experience. You could see very little math, and you could see a lot, and everything in between, although it's not common in the beginning of your career to see the advanced math. So whether you are saying, I don't like math, should I do engineering, or I love math, do you use it a lot in engineering? There's good news in both cases, and I'm going to address both of these at the end. But first, let's look at some examples. As a mechanical engineer, you're going to take a class on mechanical vibrations, where you mathematically determine the equations of a vibrating system, the maximum displacement, natural frequency, and so on. And this is a very math-intensive course. You'll be applying lots of formulas and doing problems that can be done by hand, not quickly, but in a reasonable amount of time, of course. This is important because when an engine is running or an earthquake shakes a building, vibrations occur and we need to make sure the structure or device doesn't collapse. But in the real world, when you are working on the design of something like a bridge, let's say, you want to test how it will stand up to vibrations before you make it. You are not going to take out a few sheets of paper and start writing out and solving all the differential equations that you learned in class. You model the object on the computer using software and have it do all the math for you to tell you the stress, forces, and so on along the object's surface. You still have to know the foundations of what you're looking at, and you may have to make adjustments if the specifications are not complete. You could do some hand analysis on forces on the beams if it's simple enough, but again, the complicated math is left to the computer. This is called finite element analysis, which can do vibrations, heat flow, fluid flow, forces, and more. Or in school as a mechanical or aerospace engineer, you would learn a lot about aerodynamics and equations that represent fluid flow. Like maybe you'd have to use calculus to find the drag on an object of some ideal shape, and even a more complicated shape, there would be ways to solve it by hand. And this involves a lot of math. But in the real world, for a large aircraft, let's say, you aren't about to use those equations to solve for the fluid flow and interactions along the aircraft. So we use computational fluid dynamics, in which computers perform the math for us to simulate the interactions of fluids across various surfaces. This can be used in a lot of applications. Again, you still have to understand the math fundamentally and know how to apply it, but the tedious math to find that airflow is left to the computer. Or let's say in biomedical engineering, what if you're trying to measure the force throughout someone's leg as they walk? Well, the college version of this question would be like someone's foot exerts a force straight down, and the knee is bent at a certain angle, and so on. You'd be given everything you need, and everything would be more ideal. Then you could solve for force or torque at different parts. This is actually more of a mechanical engineering question that involves statics and could involve dynamics. But in the real world, it doesn't work out so nicely, and you aren't about to do all the math on paper. You would use a walking gait that would measure the force for you as someone walks, then the software would do the math to give you the forces you're looking for. But again, you still have to understand fundamentally what is going on. And if you're trying to make, let's say, a hip transplant that has to withstand a certain amount of force throughout someone's leg, then you need to apply that math and knowledge to the structure. But the tedious math is again left to the software. Or in electrical engineering, some students may go into antenna design. This isn't popular compared to other concentrations, but I picked it because the math is pretty crazy. You may be surprised just how much math and analysis goes into solving for the electric field from the simplest type of antenna. And in usually a graduate level class, you would be asked to set up and solve these equations. But when you're designing an antenna for a company, we have software perform that math for us from the antenna we model. This would be something like HFSS, a software for antennas and electromagnetic waves. The math you did in class from above would be what the computer is doing in the background after you model the antenna. So what if you get a job in testing? This is another path you can go as an engineer where you actually test the physical product instead of creating it on the computer. Well, in the electrical engineering example, you would put the antenna in a chamber and a receiver would measure the signal. Now you see this here? This turns the antenna over different thetas or phis or whatever direction the chamber is set up for, which is where coordinate systems come in. You may need to know how to go from one to another, for example. Also, the software might give you the X component and the Y component of the signal. So to plot these values over theta, you'd have to plot the magnitude. And then you'd get that plot where you'd have to understand mathematically what that represents. See how there's definitely math? But the people doing the testing are not going to the whiteboard and doing all the calculus and analysis like they did in school. It wouldn't be possible for an antenna like this. But they apply the foundations. And if something is wrong and you don't have a good mathematical foundation, you'd be in trouble when it came to troubleshooting the issue. I know this is technical, but this was an actual example of a student's job right out of school. It's a simple example, and people in this concentration typically see way more math. But hopefully you're getting the idea of the math in school versus out of school. So again, when you're at your job and you're doing math, it's more algebra and linear algebra, trigonometry, statistics, and so on. Like, you'll definitely hear of structural engineers who do hand calculations a good amount of the time to determine loads on structural elements and how one beam may influence others. This is normally done by hand because they are either checking what the program has output, or it's a simple calculation that's faster than going to the computer. Or I've seen mechanical engineers who need to be able to do hand analysis on fluid flow, stress, velocity, etc. But again, it's mostly algebra or trig math. Anything too complicated would be left to the computer. I even heard of a computer engineer who had to work with an optical sensor, like the one your computer mouse uses, and the sensor would give only change in Y and change in X coordinates as it moved, which would be sent to the computer. So to find the total distance traveled, they had to apply the Pythagorean theorem, or the distance formula, into their program so they could keep track of the mouse as it moves. This is a small example and is actually just an internship position, but it is something. But remember, this is all general cases. There are engineers out there who do way more advanced math, especially later on in your career you can go into more of the design work, which can become very math heavy. But it's up to you to choose a path that fits you best. Now for those who love math and are thinking the more math the better, then make sure to pursue careers that involve more intensive math. You have to look around, and in the beginning it may be tough to find something. One thing to think of going into is research, whether it be for a tech company, a government lab, or a university. If you want to create the technologies and designs of tomorrow, there will be a lot of math. Whether it be quantum computers, self-driving cars, or artificial intelligence, creating new systems can be very math heavy. Very often these are people with PhDs. It's not true for everyone, and I've seen people with bachelors in these positions or on engineering design teams, but you really have to work your way up before seeing those. So don't expect it anytime soon right out of school. These projects aren't abundant in jobs, but they are out there and you should be aware of everything there is. Now for those who are saying, I'm not good at math, should I do engineering? You're not alone. A lot of people say this. Now I have always thought you should be good at math if you want to go into engineering. College alone will especially be rough if you're not good at it. And I continue to have this belief. But there are different levels of not being good at math. And if you have an interest for the subject, then you should be willing to work harder to learn it. I've seen people who struggle with math a lot. They work twice as hard as many other students just to pass their classes and still had to retake some. But they made it through and they got a job afterwards. Now this is more of the exception, but it happens. But also, engineering isn't for everyone. Every semester students drop out because it's just too much. You need to really look into what a major entails to make a confident decision for yourself. But as a little motivation for those who are hesitant, I can tell you that whatever your reasoning is for not wanting to do engineering, common one being not being good at math, I promise you that someone who was no smarter than you had that same excuse and graduated in engineering and got a job. People who graduate in engineering aren't all geniuses. Look around and you'll hear a million different stories. And after you graduate, that math you are so scared of might mostly be gone. You still need to use some and need to have a foundation, but it's just not as intense. You should be realistic and make sure you have an interest in what you're pursuing. Just ask yourself, is this something you're willing to do? Are you willing to work hard, maybe harder than most, to learn the material and get the degree so you can do what you enjoy? Now I'm going to stop there. For those watching who are in engineering or have even had internships, go ahead and comment below your experience with math and technical work at your job so others without experience can get an idea for what to expect. Everyone has their own story and it will help to hear as many as possible. If you like this video, don't forget to like and subscribe, and I'll see you guys next time.